My name is Prabjot.
My name is Rabo.
And my name is Kisak.
And hello, my name is Lavin. Yeah, and my name is Karam.
Okay, so hi everyone. I will be talking about the first two lessons of Unit 4, which is the relationship between lines and planes. And our first lesson is the intersection between two lines. And this concept is fairly straightforward and easy. I'll look at two space first, and there's three cases we can have two space. One, parallel and coincident, meaning they both lie on each other, so we have infinite solutions like this. Our second could be parallel and distinct, meaning lines are parallel but they don't lie on each other, so there's no solution. So we have one line here and one line here. And our third case could be point of intersection, meaning lines are not parallel, so there's one solution like this. If we look at three space now, there's nothing too much different. It's basically the same cases as R2, but with addition of skew lines, which are lines that do not intersect and are not parallel, so like this. This basically means they're on different planes. So I created some general steps to solve for these types of questions. Firstly, I would determine parametric equations of both lines. The next step would be to set equations equal to each other and solve for S and T values using the two equations. Simple, straightforward algebra. And in two space, plug those values into line 1's parametric equations to get your values and check to plug them into the other equation. In three space though, plug those values into the third equation to see if the left side equals the right side, and then plug the S and T value into the parametric equations to find the point of intersection. So now let's look at the next lesson, which is the intersection of a line and a plane. And again, there are three cases for this lesson. You can have the line lies on the plane, so infinite solutions. The line is parallel to the plane, so there's no solution. Or you can have a point of intersection, meaning the line and the plane are not parallel, and the line intersects the plane at one point. Some general steps to solve these type of questions would be to plug in the parametric equations of the line into the scalar equation of the plane and solve for t. If there's a value for t, and so you would sub it back into the parametric equations to solve for the point of intersection. If 0t equals 0, there are infinite solutions, meaning the line is on the plane. And if 0t equals a number, then there is no solution. So this basically covers the first two lessons, and I'll just do examples just now. Okay, so this is our example for lesson 2. We have the equation of a plane, the scalar equation, and the vector equation of a line over here, and we want to see if they intersect or not, and where if they do. So firstly, I made parametric equations of the line of x, y, and z, and then I substituted these values back into the scalar equation of the plane, like this, and just solved for t. I ended up getting t equals 5 over 8, and then I substituted that value back into the parametric equations, like this, to figure out my points of intersection, and therefore this line intersects the plane at this point. Okay, so this is our first example. We have the equations of two lines here. What I first did was make the parametric equations of each line over here and there, and I set it equal to each other. And then I solved for S and T. So what I did was I multiplied the first equation by 5, and I subtracted the first equation by the second equation, so that I'm left with 2 equals 5 minus 15s, and then I figured out that S equals 1 over 5. Then I substitute this value back into equation 1 over here, and I solve for t over here, and so I get t equals 3 over 5. But now I have to put this value and this value into the third equation to check that it works for all three equations. I did that, and I didn't get the same values. I got 22 over 5 does not equal 6 over 5, therefore
there's no solution in this example.
Alright, intersections of two planes. Lesson 3. How many ways can two planes interact? Well, there are 3 ways two planes can interact. Planes can interact by being parallel and coincident, so basically infinite number of solutions. Parallel and distinct, basically no solutions at all. They don't interact at all. And finally, intersect at a line. So they intersect at a straight line with an infinite amount of solutions. Second scenario, parallel and distinct planes. In this case, the normals are collinear, meaning n1 is equal to k times n2. However, these two planes do not intersect, meaning they don't touch at all. D values are not multiples of each other either, so d1 does not equal to k times d2. K could be any number. In this case, the diagram shows that the normals are parallel. However, the two planes are not intersecting. Here's a quick example. There's 2 lines. The normals are scalar multiples of each other. However, the d's are not scalar multiples of each other, meaning no matter what you do to the first d value, number 4, you would not get the second d value, which is 9. So d2 does not equal k times d1. Therefore, no solution. Last scenario. 2 planes intersect at a line. Normals are not collinear, meaning they're not parallel. D values do not have the same multiple either. So d1 does not equal to k times d2. Here is a diagram of it. Another example. Here, as you can see, that n1 is not a scalar multiple of n2, nor is the d values. They're not scalar multiples of each other, meaning this is no solution, and we can conclude that these 2 planes are intersecting at a line. What type of knowledge questions will be on the exam? There's only one type of knowledge question that could be asked about 2 planes. Determine the solution to the system. Given the equation of 2 planes, you have to solve the system. Alright, here's an example of intersection of 2 planes. Here we have 2 scalar equations of 2 different planes. And the goal here is to isolate for one variable. In this case, I chose y because it just looks easier. So what I did was I times the first equation by 3 and the second equation by 2. And then I got these 2 equations. Negative 6x plus 9y plus 3z plus 18 equal to 0. And the second equation is 6x minus 2y plus 4z minus 4 equals 0. I added those 2 equations together and I isolated for y. And I ended up getting negative 14 minus 7z over 7. Then I let z equal t. Once I did that, you have 2 variables. You have 2 variables that you just found. Sub in those 2 variables into any of these previous equations and isolate for the third variable. In this case, I put in negative 14 minus 7z over 7 into y, and I put t for z. And once I solved them, I got x equals negative t. That's my third variable. But you're not done yet because you didn't get the exact value of y. So what you do is sub in negative t for x and t for z, and you put it into the previous equation, and you should get what the y value is. I put it into the previous equation, isolated for y, and I got y equals negative 2 minus t. And in the end, these are your 3 points for your point of intersection of 2 planes.
Alright, I'm going to be talking about 3 planes in geometric interpretation. There are a total of 8 orientations. The first 5 below have parallel planes, which can be determined by the normals and the d values of the system of equations. The following 5 orientations have parallel planes. And this chart that was given to us in class lists the geometrical interpretation, the diagram, type of intersection, and what to look for in the system of equations when trying to figure out whether or not the orientation is parallel. There are also three orientations in which planes are not parallel. This means that the planes either form the shape of a star, triangular prism, or all intersect at one point. These three examples are also from the handout that was given to us in class. The first is a triangular prism, the second is a star, and the third is where they all intersect at one point. Lastly, we'll look at two examples. In the first example, we'll look at systems that involve parallel lines. In the second example, we'll be looking at a system that is not parallel. Okay, this is example 1. It says, state the geometrical interpretation of the following system. So, to start off, I'm going to start by writing the normals of each system. Now that we have the normals, we have to try and see if there's any similarities between any of the three normals. By looking at the normals 1 and 2, I can see that normal 2 is a multiple of normal 1. 4 times normal 1 would give you normal 2. Now we have to compare the d value of both normal 1 and normal 2. When you compare 4 and 32, you don't really see a comparison. So 4 times d1 does not equal d2. Next, I look at n1 and n3. There I can also see a common multiple, which is -3. So -3 times n1 is equal to n3. Now when I look at the d values of both n1 and n3, 4 and 17, I don't see another similarity. So -3 d1 does not equal d3. Based on this, when we look back at our given chart, we can state that the geometrical interpretation of the following system is 3 parallel and distinct planes.
Bang, bang.
Example 2. It says, state the type of intersection of the following system. So to start off, what I did was write down the normals. Now, based on the normals that I've just written down, I try and compare to see if any of the normals have anything in common or have any similarities to see if they're parallel. But because there's nothing really in common, we can say that they're not parallel. So we can use n1 dot n2 cross n3. So you start off by doing the cross product between n2 and n3, which I did on a separate piece of paper, and the answer I got was -24, 0, 8. So now we do the dot product, and once we do the dot product, we get -24 plus 0 plus 24. This gives us equal to 0. This 0 can mean a lot of things. As you know, there are 3 non-parallel solutions. One of the first solutions is when it is not equal to 0 over here. If it's not equal to 0, the solution is a point. It's when all the planes intersect at one certain point. If the solution is a 0 like we have here, when we eliminate for our variables, we'll get either 0 is equal to a number, which means it is a triangular prism, meaning that there is no solution, or we'll get 0 is equal to 0. This means that it is a star, and the solution is a line. So Now we move ahead and try and figure out whether it's a triangular prism or a star. So in order to do that, what I did was first rewrite my given system of equations. Four 2x plus 6y plus 6z equal to 16. Once I did that, I named each of my equations 1, 2, and 3. Now what we're trying to do is get rid of variables. So we'll start by getting rid of x and z because it seems easily crossable here. So 4y minus 4, negative 8y is equal to negative 8. These are my new equations, 4 and 5. To get 4, what I did was take equation 1 and subtract it from equation 2. To get equation 5, what I did was 2 times equation 2 minus equation 3. Next, I took equation 4, multiplied it by negative 2, and then subtracted it by 5. And the answer I got was 0 is equal to 0. This means that the solution represents the shape of a star. Therefore, the shape is a star, and the type of intersection is a line.
This is an example of a question for shortest distance from a point P to a line L. So the question says, find the shortest distance between the point P2, negative 1, 2, and a line negative 1, 0, 7 plus T 4, 1, negative 2. This here is an example of the question which I drew. See here, this is the point 2, negative 1, 2. And this is the line negative 1, 0, 7 plus T 4, 1, negative 2. This dotted line right here represents the shortest distance that we need to find. First step is finding the h right here. H is negative 1, 0, 7 plus T 4, 1, negative 2, which then you can replace it as negative 1, comma 4t, comma t 7 minus 2t. Then using that h point, you find ph, vector ph. So ph is represented as negative 1, 4t, t 7 minus t minus point p, which is 2, negative 1, 2. Now, having the vector ph, we need to find t. Therefore, we need to do a dot product. Dot product of ph and 4, 1, and negative 2 is 0. 4, 1, negative 2, we got that from because ph is perpendicular to the direction vector of 4, 1, and negative 2 of the line L. So, negative 3 plus 4t plus 1t, 5 minus t, dot product of 4, 1, negative 2 results as t equals 1. You sub that t back into the each point, find h, which is 3, 1, and 5. Then you find ph, which is 1, 2, and 3. Then find the shortest distance of OH, which is square root of 1, 4, and 9, results as 3.74.